We are going to switch gears now and start talking about systems of equations. So the idea is that in practice, we usually don't just keeping track of one thing, but many things, and many things interact. And the way we do this is working with systems, and we need a vital tool, linear algebra, to help us work with systems. So we're going to back up, talk about linear algebra, and then come back and start looking at differential equations shortly. Before we do that, we're going to look at a couple definitions. You should be familiar with this or have seen these before. And the idea is, first is what is a vector? A vector is just something that has direction and magnitude. And we, in this class, are going to express these as column vectors. So the idea is it's just a column of numbers. So an example would be something like this has 3 dimensions. So I can think of this as the x dimension, the y dimension, and the z direction. In general, if I have n numbers, so I have v1, v2 to vn, we would say this is a number in Rn. Each of these are real numbers. Well, later on, we're going to see what happens when we have complex numbers. This is just in different directions. And think of it as just a collection of n numbers. What's going to be important for us is something called the dot product. So in this case, suppose we have 2 vectors with n rows. So this is going to be u1, u2 to un, and another vector v, and it has n entries. We're going to need the dot product. So the idea behind the dot product, u dot v, so I've got the u1, u2 to un dotted with v1, v2 to vn. I'm just going to go entry by entry. I'm going to take this times this, and then I'm going to add this times this and keep going down. So we're defining this to be u1 times u2, that's u1 times v1 plus u2 times v2 plus u3 times v3, and you keep doing that till you get to the very last entries. So you get un times vn. All right, and what's important about this is that u dot v has an important geometric interpretation. In particular, we're going to need another idea. So if we have a vector u, we want to talk about the length of the vector, and we're going to denote the length of the vector in this form. So be careful. This is a little different in the physics department. In the physics department, they would use this notation. We do not use this because it gets confused with the absolute value. So we will not use this. We use the 2 things. And we can think of this, so if we have a vector u, then this is going to be the length, or how long that vector is. Right, so for example, if u is the vector 3 minus 1, then if I go 1, 2, 3 in the x direction, down 1 in the y direction, so that's the vector u. Then I can think of this as like a triangle. That length is 3, and that's going to be a length 1. The length of u, or the norm of u, is going to be the square root of 3 squared plus minus 1 squared. That's basically the Pythagorean theorem. And we can generalize this into higher dimensions, and it turns out to follow the same pattern. So if I have a vector v, then its length is going to be the square root of v1 squared plus v2 squared plus v3 squared, all the way out to the last one, like so. And one thing to notice is that I can think of v1 squared as v1 times v1, v2 squared is v2 times v2, v3 squared is v3 times v3, blah, blah, blah. This last term becomes vn times vn. This is v dotted with itself, v dot v. So we're going to define the norm to be the square root of the vector dotted with itself. Okay. So for example, if I have a vector x, and the vector is 2, 4, minus 1, the norm of x then is going to be the square root of x dotted with x. So x dotted with x is going to be 2 times 2 plus 4 times 4 plus minus 1 times minus 1. It's going to be the square root of 4 plus 16 plus 1. It's going to be what? Square root of 21. So the length of that vector is 21. And geometrically, we can interpret this thing in terms of for the dot product. Is if I have two vectors u and v, and I find the dot product, that is the same as the norm of u times the norm of v times the cosine of the angle between them. So if that's a vector u, and this is a vector v, there's going to be some angle between them. If I project this down for a right angle, then this distance right here, that is the length of u times the cosine of theta, right? Because this length is the norm of u. Okay, we're not going to go into the details and prove this. You should have seen this in your Calc 3 class, or you will see it in your Calc 3 class if you haven't taken it. But we don't want to get wrapped up in those details just yet. But for now, you should be able to take a dot product of two vectors. So for example, if I tell you u is 3 minus 1, 4, and v is 4, 0, minus 3, then u dot v is going to be 3 times 4, so that entry times entry, plus minus 1 times 0, so the two middle entries multiplied, plus 4 times minus 3. That's going to give me 12 plus 0 plus a negative 12. That is 0. Now what does that mean? So that we just found that u dot v is 0, but we also know that it's equal to the norm of u times the norm of v times the cosine of theta. In this case, the norm of u is not 0, the norm of v is not 0. So that means the cosine of theta is 0. So if I tell you the cosine of an angle is 0, right, that basically means then that theta is going to be pi over 2 or 3 pi over 2, and that means that u and v are at right angles to one another. Okay. So if we have the u and v are at right angles, we are going to say u and v are orthogonal to one another. Right. Another way to say that is if u dot v is 0, then u is orthogonal to v, where v is also orthogonal to u. Okay. Now, so we have this definition. Given two vectors, we can basically do this calculation and we can give it some geometric interpretation, because u dot v is equal to the length of u times the length of v, or I would say the norm of u times the norm of v times the cosine of the angle between it, the two vectors. That we're going to build on this idea in terms of looking at structures that are not just column vectors or row vectors. In particular, we want to look at linear systems. Our goal later on is to be able to work with systems of equations. So for example, suppose I have 3x plus 2y is 7, and and I have 4x minus y is 1. Then we are going to express this in a different form in terms of matrices and vectors. And the idea is I want to write it as a matrix times a vector is equal to a vector. And the way these are all going to be definitions, and there's a lot of definitions and a lot of relationships, and it's really important to go back and look at how these things are defined, because there's some real issues here with horses and carts. So this is our linear system, and an equivalent way to write this is the following, and we'll get into the details of this and why this works. But we're going to work, our unknowns here are x and y, so that's going to be an unknown vector, and we have a known vector on the right, 7, 1, and the coefficients here we're going to write in this form. And what this implies is that the definition here is that when we have a matrix, so we're going to call this a 2 by 2 matrix. It has 2 rows, row 1, row 2, which is this first 2, and it has 2 columns, which is represented by the second 2, this first column and the second column. And the way we're going to define this operation, this is a matrix, and this is going to be a vector. So this is a 2 by 1 vector, and this is 2 by 1. So it has 2 rows, 1 column. We're going to go across. So I have 3 times x plus 2 times y is going to be that entry. And then for the second row, I'm going to go across the second row, 4 minus 1. So I'll have 4 times x plus minus 1 times y is 1. And these two expressions are exactly the same. It's going to turn out that writing things in this form is going to give us some tools that are going to allow us to work with these in a much more profound way. And working with this, we can throw this is going to be much more convenient to be putting on a computer and having the computer solve systems. So what do we have? We're going to have a matrix. It's just an array of numbers. These numbers are going to be arranged in rows and columns. And we have vectors. And this is basically a matrix with 1 column. Or we're going to see situations where it's going to be just 1 row. So a column vector is going to be a set of numbers written like this. And a row vector is going to be a bunch of numbers arranged in a row. Okay, and it's important to recognize that even though these numbers are the same, these are different things because we cannot compare a column vector to a row vector. They're just different. But if we have things that are like, so we have the same number of rows and columns, then we can do things like add and subtract. So if we have a matrix and we want to add things, so for example, if I have 2 by 2 matrices, I can add them, and I'm just going to go entry by entry. So for the first row, first column, I'm just going to add first row and first column. So 3 plus 7 is 10. For the first row, second column, I'm going to go minus 1 plus 6 is 5. For the second row, first column, 2 plus 2 is 4. And the second row, second column is going to be 4 plus 1 is 5. We can also do scalar multiplication. And the idea here is if I've got a matrix, if I have a scalar number outside, I'm just going to multiply every number by that number. So I got 4 times 3 is 12, 4 times minus 1 is minus 4, 4 times 2 is 8, and 4 times 4 is 16. Now we're going to define something called matrix multiplication. And in order to do this is going to be just a definition, and it turns out that this particular definition is extremely useful. And we're going to define this in terms of matrix multiplication. It's going to be important to be able to look at a matrix. So for example, we have a matrix with 2 rows and 3 columns. So we would say this is a 2 by 3 matrix. We need to be able to look at this in different ways. One way is to look at it in terms of row vectors. So we can think of this as 2 row vectors, where U1 is going to be 8, 7, 3. And U2 is the second row, is 6, 5, 4. We also have to be able to look at this in terms of column vectors. So we could think of this as V1, V2, V3, where V1 is the first column, V2 is the second column, and V3 is the third column. And we have to be able to go back and forth and think about this in these different representations. Okay. Now, in terms of notation, I got to be very careful. We've defined things like dot products as column vectors, and these are row vectors. And I'm going to make a slight change in this notation. The notation is going to start getting very thick and very complicated very quickly. So it's important to just step back and think about this notation. So we've seen things like this. Just if I have U by itself, this can be very confusing, especially in this class, because sometimes it's a number. Sometimes it's a function. So for example, it might be cosine of t. And now all of a sudden we're working with this thing as a vector. So this notation is going to be extremely important. If you forget that little hat, then it's not a vector. So these things are vectors. These are not vectors. They are different. And if you forget that hat, you have a big issue. This is further complicated because in the book, and many books, unfortunately, we don't necessarily use these hats. We write these in bold font. And if you see something in bold font, that means it's a vector, which is extremely confusing, especially when you're writing on paper. You can't just change the font. So using this hat is going to be extremely important. And we're also going to need something called a transpose. And the idea behind a transpose is we just flip it so that if you have a column vector, it becomes a row vector. If you have a row vector, it becomes a column vector. So for example, if U is a column vector, and I take its transpose, so in this case, U is a column vector, 7, 2, 4, and I take its transpose, and the notation is this thing, I'm basically just going to flip it on its side. So this becomes 7, 2, 4, and this is now a row vector. Likewise, suppose V is a row vector, and I take its transpose. So it's going to be treating T as a superscript. It's going to flip it so that it's now a column. And the first column becomes the first row. Second column becomes the second row. Third column becomes the third row. So why is that important? We're going to define matrix multiplication in terms of treating matrices as columns and rows and dot products. And in order to use dot products, we're going to think of these as transposes. So for example, so I've got matrix multiplication. If I have matrix A times B, I'm treating A as a matrix. Suppose it has m columns and n rows. And so it's going to have n1, n2, n3. So this is an n by m matrix. And so suppose B is going to have m rows. And suppose it goes out to have k columns. Let me see that. Sorry. This is going to be 2k mk. So this is going to be now, we have m rows and k columns. I want to be able to multiply these things. And many of you should have seen this. The idea is I'm going to go across the row of the first matrix and down corresponding columns of the second matrix. And I'm going to take a dot product. So I'm going to take this number times this number plus this number times this number and add those up. So to do that, first of all, the number of columns for the first matrix has to equal the number of rows for the second matrix. And basically this is a dot product. So if I take A times B, I am now, what I'm doing is I'm thinking about A as a series of row vectors. So I have the first row is going to be A1 transpose. So if A1 is a column vector, I take its transpose, it's going to be a vector across the first row. Second row is going to be called A2 transpose. And then the last row is AN transpose. So this, thinking of these as row vectors, represents a n by m matrix. These are the same things. And now I'm thinking of the B matrix as a bunch of column vectors. So the first column is going to be B1, second column is B2, and the last column is BK. And I'm going to define matrix multiplication. The first entry here in the first row is going to be A1 dotted with B1. Second row is going to be A1 dotted with B2, and it's going to go all the way across. Oops, these are dotted. And now for the second row, it's going to be the exact same thing, only instead of A1, I'm going to use A2. So I'm going to take A2 dotted with B1, A2 dotted with B2, all the way out. And then the last row is going to be the same, but using AN. So AN dotted with B1, AN dotted with B2, and then the very last entry is going to be AN dotted with BK. Oops, and I screwed up. That should be BK, or vector BK. So another way to, let's just do an example, because this is really thick. So for example, if I have the matrix 2, 4, 7, 6, and the matrix 2, 1, 3, minus 2, 1, 4, I can multiply these matrices. So what am I going to do is I'm going to get this entry, I'm going to go across the first row and down the first column. So I'll have 2 times 2 plus 7 times, so 2 times 2 plus 7 times minus 2. So that's 4 minus 14 is minus 10. For this entry, as I go across here and here, I'm still going to use this first row of the first matrix, but I'm going to use the second column and then the third column. So I'm going to have 2 times 1 plus 7 times 1 is 9. And in this entry, I'm going to have 2 times 3 plus 7 times 4. So it's 2 times 3 plus 7 times 4. So that's 6 plus 28 is 34. Okay, is that right? That doesn't seem right. So 6 plus 28, I guess that's right. Okay. Now, as I go across the second row, I'm going to do exactly the same thing, but I'm going to use the second row of the first. So this entry is going to be 4, 6. I'm going to use the first column. Second column here is going to use the second column and across. So I'm going to have 4 times 2 is 8. And then plus 6 times 2 is minus 12. So that's 8 minus 12 is minus 4. For here, I'm going to go across the second row down here. So that's 4 times 1 plus 6 times 1 is 10. And then the last row, that's going to be 4 times 3 plus 6 times 4 is 24. So that's going to be what? 36. Okay. So notice I had a 2 by 2 matrix multiplying by a 2 rows by 3 columns. The number of columns is equal to the number of rows, so I can do it. And I can just go through and do that multiplication. Now, notice there's going to be a special matrix. And this special matrix is going to have all zeros on it. Except the diagonals, and the diagonal entries are all 1s. And so this is all zeros, except the diagonals equal 1. This is going to be called the identity matrix. Okay, and what's special about this is that this matrix times any matrix just gives you the other matrix. So for example, if I have the matrix 3, 4, 2, minus 5, 6, 7, 8, 7, 0. Now an identity matrix has to be square because the diagonal entries are all 1s. So this is going to be have 3 rows because there's 3 columns. So put 1s on the diagonals, everything else is zeros. So I'm going to have 3 times 1 plus 4 times 0 plus 2 times 0 is 3. For this entry, I'm going to go across the first row down the second column. 3 times 0 plus 4 times 1 plus 2 times 0 is 4. And then for the third column in the first row, 3 times 0 plus 4 times 0 plus 2 times 1. And then likewise, I'm going to do the same thing across second row, but the only difference is I'm going to use the second row in the first matrix. So minus 5 plus 0 plus 0, 0 plus 6 plus 0, 0 plus 0 plus 7. And now as I go across the bottom row, I'm going to use the third row of the first matrix. So I'll have 8 plus 0 plus 0, 0 plus 7 plus 0, 0 plus 0, and 0 times 1 is 0. And notice this matrix and this matrix are identical, and that's always going to be the case, is that A times I is going to be equal to A, but also I times A equals A. And this is assuming that it's possible to do this multiplication.